Let's draw the bending moment diagram for this beam, and here we're going to release the fixed support. So if we draw in our reactions, we have one at the roller, two force reactions at the support, plus a moment reaction. So we have one extra unknown, and we can use the force method to solve for it. And here we're going to release the rotation at the fixed support. So therefore we obtain a pin at this support. And we're going to superimpose these two cases to get our compatibility condition to solve for the moment reaction. So on the first case we apply the distributed load, which results in a clockwise rotation. And for the second case, we apply our unknown moment reaction, which results in a rotation that's counterclockwise at the fixed support. And therefore our compatibility condition is the net rotation at the fixed support is 0. So we know for a simply supported beam under a uniformly distributed load, theta A is WL cubed on 24 EI. And for the second case, we're going to apply the principle of virtual work to obtain a rotation. So the real bending moment is equal to the jump being m, and it varies linearly to 0 to a 0 bending moment at the roller. And for the virtual case, we apply a virtual moment to obtain a rotation at the support. Because remember, work is moment by rotation or force by deflection. So the virtual bending moment diagram has a unit moment at the support and goes linearly to 0 at the roller. And therefore the rotation theta b is the real by the virtual moment by the length on 3 EI. So the volume between two triangles is a pyramid. And substituting these into our compatibility condition, we have theta A is WL cubed on 24 EI, and that's clockwise, so it's negative, then plus theta B, which is ML on 3 EI, and that's equal to 0. So if you solve this equation, we obtain a moment reaction is WL squared on 8. And therefore the bending moment diagram at the support has a magnitude of WL squared on 8. And at midspan, we know the bending moment diagram for a simply supported beam has a magnitude of WL squared on 8. And by similar triangles, the bending moment for this case is m on 2 at midspan, which is WL squared on 16. So therefore at midspan, we have a bending moment of WL squared on 8 minus WL squared on 16, which is WL squared on 16. And our bending moment diagram is parabolic. And note that the bending moment at midspan is not the largest positive one, as the bending moment diagram is not symmetric. Please subscribe, like and comment to help me reach more students.